When we talk about memory performance, we usually focus on two things: latency, how long you wait for data; bandwidth, how much data you can move per second. But there is a third factor that often determines real-world performance: how many memory operations can be in flight at the same time. That concept is called memory-level parallelism. In this video, we're going to explain what memory-level parallelism is, why it matters, how it interacts with latency and bandwidth, and why modern CPUs rely on it to keep performance high. Let's begin with a simple problem. Main memory is slow compared to the CPU. Accessing RAM can take hundreds of cycles. If a processor issued one memory request and then waited for it to complete before issuing the next, performance would be terrible. The CPU would stall repeatedly. Memory-level parallelism solves this by allowing multiple independent memory requests to be outstanding at the same time. Instead of waiting for one load to complete, the processor can issue several loads simultaneously. While one request is traveling to memory and back, others are already in progress. This overlaps latency. Now let's clarify something important. Memory-level parallelism does not reduce the latency of a single memory access. Each individual access still takes the same number of cycles. But by overlapping multiple accesses, the processor reduces the overall time spent waiting. Imagine you send one package at a time through a slow delivery system. You wait for each one before sending the next. That's inefficient. Now imagine sending 10 packages at once. They still take the same delivery time individually, but you don't wait for one to finish before starting the next. That's memory-level parallelism. Now let's connect this to out-of-order execution. Modern CPUs maintain structures that track many in-flight instructions. If several load instructions are independent, meaning they do not depend on each other's results, the processor can issue them in parallel. These requests are sent to the memory subsystem. The memory controller handles them, possibly reordering them for efficiency. When the data returns, the CPU resumes dependent instructions. This ability to track and manage multiple outstanding memory requests is critical for performance. Now let's talk about independence. Memory-level parallelism only works if loads are independent. Consider this example. You load a pointer from memory. Then you use that pointer to load another value. Then you use that value to load another pointer. Each load depends on the previous one. You cannot issue the second load until the first completes. This is called a dependent memory chain. In this case, memory-level parallelism is limited. You are forced to wait for each access in sequence. Now compare that to this example. You are iterating through multiple arrays at once. Each array access is independent. The CPU can issue several loads in parallel. This increases the number of memory requests in flight and improves overall throughput. Now let's connect memory-level parallelism to bandwidth. If you only issue one memory request at a time, you may not fully utilize available bandwidth. Memory systems are designed to handle multiple concurrent requests. By issuing several loads simultaneously, the CPU increases effective bandwidth usage. So memory-level parallelism helps both latency hiding and bandwidth utilization. Now let's discuss hardware limits. Processors have a limit on how many memory requests they can track at once. This depends on internal buffers such as load queues, store queues, and miss status handling registers. Once those structures are full, additional memory requests must wait. This creates a ceiling on memory-level parallelism. So even if your program has many independent loads, hardware resources may limit how many can be active simultaneously. Now let's connect this to multi-core systems. Multiple cores may each generate their own memory requests. From the perspective of the memory controller, all these requests compete for bandwidth. High memory-level parallelism across cores can saturate memory bandwidth. This is why scaling performance across cores sometimes hits a memory bottleneck. Now let's talk about practical software implications. Programs that process data in independent chunks tend to benefit from memory-level parallelism. Batch processing, vectorized loops, parallel algorithms, these allow multiple loads to be issued without strict dependencies. In contrast, pointer-heavy structures like linked lists or tree traversals often limit memory-level parallelism. Each node depends on the previous node's address. This forces serialized memory accesses. As a result, performance may be dominated by memory latency. Now let's connect everything. Caches reduce average latency. Latency defines how long each memory access takes. Bandwidth defines how much data can flow per second. Memory-level parallelism defines how many memory accesses can be overlapped at once. Together, these three determine memory performance. If latency is high, but memory-level parallelism is also high, the CPU can hide much of the delay. If latency is high and parallelism is low, performance suffers. If bandwidth is high but parallelism is low, available throughput may go unused. All three must work together. Now let's zoom out to the broader execution model. Instruction dispatch selects work. Branch prediction keeps control flow smooth. Pipelines overlap instruction stages. Out-of-order execution rearranges independent instructions. Superscalar execution issues multiple instructions per cycle. SIMD processes multiple data elements per instruction. Caches reduce average access time. Memory latency defines delay. Memory bandwidth defines throughput. Memory-level parallelism defines overlap. Modern CPU performance is the result of all these layers working together. If you understand memory-level parallelism, you understand why some programs scale well and others don't. You understand why dependent memory chains are dangerous. And you understand why structuring data and algorithms to increase independence can dramatically improve performance. If you want to continue deeper into memory systems, the next logical step is cache coherence in multi-core systems, or exploring how virtual memory and address translation affect performance. But for now, you can summarize memory-level parallelism like this. Memory-level parallelism is the ability of a processor to issue and handle multiple independent memory requests simultaneously, overlapping latency to improve overall performance. And in modern systems, that overlap is essential.